In this video, we'll be going over a few calculations for strong acids and strong bases. So when we do these acid-base problems, whether it's a mixture or just a single acid or just a single base, whether you have grams, whether you're given volume and molarity, etc. One thing is going to be consistent. You'll have, let's say, uh, our beaker, and let's say you have like a mixture of acids. So this will be like from like HCl is added, okay, and maybe some more hydronium or H plus is added from like HNO3. So you might have multiple sources of hydronium, but the key thing is that if you're asked to calculate a pH, it's the negative log of the H plus concentration. So don't forget that those brackets, it means molarity, which is kind of useless actually. The capital M is moles per liter. Okay, and we have to be real accurate about what we're defining as our moles per liter. So it's our moles of H plus over our total liters of solution. Okay, so now if you're asked to calculate the pH for a base problem, okay, then we're going to use water's kW to figure out. You could get the pOH and subtract from 14 is usually how I do it. So let's say you have like NaOH. Okay, so that's going to give us some OH that will come in, and let's say you have like 10 grams of like calcium hydroxide. So that's also going to enter this picture. So when we do this problem again, pH is the negative log of H plus. So if we solve this problem, we're going to go like this. We're going to try to get OH first, because this is easy. That part's easy. You could just go the pH equals 14 minus the pOH. So we can get minus the pOH. Okay, and then the pOH is going to be the negative log of the hydroxide concentration. So the key to doing this problem then is to get the moles of this and then the moles provided by this, so that we can get if we get that, then we'll have our total moles of OH divided by the total volume of solution. So the thing about this is we're going to try to get this. Okay, although the question is asking calculate the pH, this is really the key. Because once we get this, we'll get the moles generated by that and the moles generated by that. Then we could take the negative log of this number and then subtract from 14. Okay, and then we'll have our pH for base problems. Okay, so let's get started. Let's do a couple examples. So the first one I have is a simple strong acid example. So we have this. So remember, strong acids, this is totally different than how you do weak acid problems, and this is one of the several reasons why you want to have these memorized, is the H plus and the NO3 are totally going to dissociate. So if you had an ice table, okay, this is going to be the initial amount is 1.60 times 10 to the negative third. Now all of it, that means minus 1.60 times 10 negative third, all of it goes, so these are zeros at the beginning, all of it goes over here, 1.60 times 10 negative third. This is 1.60 times 10 negative third. Okay, so and then the amount here at equilibrium is 0. Again, that's why we don't have Kas, right? So we have, if we try to write an expression, it would look something like this. This would be over 0, so which is undefined. So that's the key with really this one of the underlying things why all these work in this whole video. So this is our amount of H plus, and remember our pH is the negative log of that number. So in this case, it would be this. So again, the reason I wrote this all out is just to show you that all of this goes here. So that's our negative log, because we could just pull our calculator and go boom, negative log of that, and that's our answer. But I just wanted to go over why you can do that. So it's 100% dissociation is why we can do that. So I have now, this is 3 sig figs, so 3 sig figs. So our answer should have 3 decimal places. So my calculator says 2.796 for that. And then the pH is, of course, unitless. So that's the answer. Okay, on to the next problem. So here we have a mixture of acids. So we have 90 milliliters of 5 molar HCl, and this is mixed with 30 milliliters of 8 molar nitric acid. So like I was explaining in the beginning, we need our, so pH, this is simple enough, is going to be the concentration of H plus. Okay, so this is kind of just robotically memorizing, but what do these mean, these brackets? It means the concentration, so we need our total moles of H plus over the total volume. Okay, and it's best done if we imagine a picture here. Okay, just like at the beginning of this. So we're going to have a source from HCl. It's going to add some H pluses. And then we're going to have HNO3 add some H pluses. Okay, and so we need to get those total volumes. So this is going to maybe, like the HCl will bring it, let's see, that's 90 milliliters. So that's 90 is going to be from that. Some H pluses from there. And then you're going to have another 30 for the HNO3. So our HNO3 is going to add another 30. So that might be like up to here. So this will add some H pluses. Okay, so we want to calculate, we want to get this grand total here and put that here, and then add up the volumes, and then that goes here. Okay, and then we have accurately defined how we're going to solve this, or what this problem depends on. So our total moles of H plus is going to be 90.0 times 10 to the negative third liters times 5.00 moles per liter. This is from the H plus. So this is from, I meant to, I meant to keep these colors consistent. Sorry about that. So let me do that real fast. So we have 90.0 times 10 to the negative third liters times 5.00 moles per liter. And this is from the HCl, from this guy. Okay, and we're going to add this to the amount from the HNO3. So this is 30.0 times 10 to the negative third liters. So we're going to change this to moles. 8.00 moles of H plus from the HNO3 per liter. So we're going to add those two together. Okay, and divide by our total volume. So our total volume was 90, or we could go 120. So we're going to add 90 and 30. So 120.0 times 10 to the negative third liters. Okay, so this gives us our H plus. This will be I suppose I don't have that number handy. So 90 times 5. So this is 0.45. And this is 0.24. So I'm going to add those both and divide that by 120 milliliters. So I get 5.75 molar H plus, and it says calculate the OH concentration. So OH is going to be KW over H. So that will be 1 point, so it should have 3 sig figs, 1.74, 10 to the negative 15th molar. And we also need the pH. So the pH is going to be the negative log of that number. And I think, yeah, I'm going to wind up with a negative because we have a log is greater than 1. So 5.75. Okay, and I have a negative 0.7. So I have 3 sig figs, so I should have 3 decimal places. 0.75, 0.760 is the pH. Okay, on to the next one. Okay, so we have a couple different, so we have a base example now. Okay, so we have 0.1 molar NaOH. So for part A, I have 0.1 molar NaOH. So that means, so this NaOH will fully dissociate and it's going to make Na plus OH. And so my OH concentration is the NaOH concentration because it fully dissociates. So this is going to be 0.10 molar. So now in this question, I'm just asked to calculate the pH. So the pH is going to be 14 minus the negative log of the this is the POH. 14 minus the POH, the negative log of 0.10. Okay, you should kind of actually do this separately in your calculator because you're going to apply 2 sig fig rules, one after the other. So you kind of have to write this number out. So negative log of 0.1 is going to be 1. So, but the reason is I need to apply the sig fig rule. So I should have 2 sig figs. So this is 2 sig figs. So my answer here should have 2 decimal places. So this should be 1.00. Okay, and then when we subtract 14, this 14 is exact. So it should not limit my answer. So my answer should have 2 sig figs. So this should be 13.00 for that one. Okay, and then for B, my concentration is going to be 1.0 times 10 to the negative 10th molar. So the negative log, this is my POH of that number, is going to be 10. So, but I should have, that's 2 sig figs, so it should be 10.00, 2 decimal places. So that's my POH, so I'm going to subtract 14 from that. And that gives me 3.00 for the pH. So notice that since this is super low, that means you have an acidic solution. So C is a mixture. So I'm going to have 2 molar NaOH, and I'm going to have 10 grams of BaOH2. So my 2 molar NaOH is going to be 2, so I'd say it's telling me I have a liter of the NaOH. So 2 molar NaOH is going to be 2 moles. Okay, so it's just this times 1 liter. So that's going to be 2 moles of OH. Okay, next I want to get the amount of the moles of OH from the BaOH. So this is 10 grams of BaOH. My molar mass is 171. So 1 mole of BaOH2 is 171.4 grams. And this is going to generate 2 OHs per mole of compound. So this is going to be, what did I get for this? I got 0.117 moles, 17 moles of OH from this. Okay, so I'm going to add those. So my concentration of OH is 2.0 plus the 0.117, which is, because of sig fig rules, 2.1 moles of OH. Okay, and it's dissolved. This is all happening in 1 liter of solution. So I'm out of space, so I'm going to write way up here. And again, I'm going to take the negative log. So my POH is the negative log of 2.1. I'm going to end up with a negative, which is possible. So I'm going to get negative 0.3, let's see, 2 sig figs, so 2 decimals, 0.32. Okay, so then my pH is going to be 14 minus that number, negative 0.32. So this is actually going to be 14.32, the pH for part C. Okay, on to the your turn. So this is on the next slide. Okay, so these are the your turns. So on this one, we have on part C here, notice we have a mixture. These should, A and B should be straightforward. Here is going a little bit backwards. They give you the pH, and they're asking you how would you prepare this, okay, with a 1.5 pH, and you want it to be, the desired strength is using 12 molar HCl. Okay, and how do you prepare a solution that's 1.5 pH? So that's going to be a dilution question there. And then question 3 is similar to part 1, but it's with a base, a strong base. But notice this one also asks you to calculate these 3 things for A, B, and C. Okay, that's the end of our video.